All right, Chem Kids. Well, hopefully you had some time to take a look at the notes that I posted on Google Classroom for you. It walks you through pressure, atmospheric pressure, talks a little bit about boiling point and what affects boiling point, talks a little bit about how some substances don't have any boiling point or melting point, gets into evaporation, of course, temperature, what temperature actually is, and then the kinetic theory of matter. So if you could see the molecules and the particles moving, what would they actually be doing? And then this is where we're going to spend our time today using a problem set. We're going to talk about Boyle's Law and Charles Law specifically, and then get into the combined gas law. And one thing that you may have noticed in that video is that Boyle's Law deals with pressure and volume. Okay, deals with pressure and volume. So the example that was used in the video was maybe taking a balloon and just squishing it. And of course, if you decrease the volume of that balloon, right, if you take the container that all that gas is in and smash it, then the pressure of the gas that's inside the balloon is going to increase. So Boyle's Law really says that when you have increased pressure, you have decreased volume. And you can look at that another way, right? You could also say that when you decrease the volume, right, you're going to increase the pressure. So you can look at this a couple different ways, and it just depends on the situation. And so we're going to spend a little bit of time talking about the Boyle's Law equation right here. And then we also are going to take a look at Charles' Law. And Charles' Law talks about temperature and volume. And we're assuming everything else is constant, so that the pressure is actually constant. All right, the pressure is not changing. But if you were to change temperature, well, then something's going to happen to the volume. And you've all been I'm assuming that you've all had an experience where maybe you've taken something like a balloon and you've gone outside with it, or maybe you've put it in the freezer, and what happens? Well, the balloon decreases in volume. So the opposite is true. Is if I increase my temperature, right? Let's say I take a hairdryer to my balloon, the volume will also increase. So this is different, where we have two variables here that are directly proportional, right? One goes up, the other goes up. Where over here with Boyle's Law, we have two variables that are indirectly proportional or inversely proportional, okay? So if you look at the equation for Charles' Law, you'll see that it's written differently than Boyle's Law, where here we're multiplying the variables and here we are dividing the variables. And the cool thing is we can actually take both of these laws, Boyle's Law and Charles' Law, and we can combine them and create what's called the combined gas law. So you'll notice you'll see Charles' Law right here, right? V over T. And you'll see Boyle's Law right here, P times V. So they're combined. And if we ever read a problem where maybe volume didn't exist or temperature didn't exist or wasn't included in the problem, we would just cross it off. And look, if I crossed off temperature because it wasn't included in the problem or it was constant, I would have Boyle's Law. Okay? Make these equal to one another. Or if I didn't have pressure in my problem, I could cross off pressure, and I would just have Charles' Law left over. But oftentimes when we are working with gases, right, we're going to be dealing with a pressure, a volume, a temperature. It's a bit rare that, depending on the circumstance, that you don't have all three of these involved with, let's say, a calculation. So let's take a look at a problem here together. All right, and this is problem set 28. You should be able to download this and take a look at it. All right, we're going to walk through a few of these problems together here. Okay, so I've got a sample of some gas that occupies 2.8 liters. Well, you should be able to recognize right away, liters. That is not a pressure. It's not a temperature, but that's a volume. I'm actually going to write a little V1 right above it, and you'll see why here in just a second. I also see that it says there's a pressure of 720 torr. Now, you guys need to realize a few things about units when it comes to pressure, all right? You're probably most familiar with the units PSI. So we can have pressure units be in pounds per square inch, right? We can have pressure units be in what are called millimeters of mercury, and I'll explain this in our class when we meet. We can also have pressure units be in kilopascals. So we would have kilopascals. And there's another word that you'll hear that is called a torr, T-O-R-R. And that is the same as a millimeter of mercury. They're the same thing. So at sea level, and you may already know this, right? At sea level, the pressure per square inch is 14.7 psi. That means that if you were to draw a square inch on your hand, this is about a square inch right here, okay? If you were to draw a square inch on the back of your hand, you would actually have about 14.7 pounds of pressure from the air pushing on that square inch. Think about all the square inches on your body, all right? Your body is used to, and let's just round this up to 15, your body is used to about 15 pounds of pressure on every square inch of your body. It's a big deal. And you're used to feeling pressure if you've ever dove into a pool and went deep. Maybe you were down in the deep end or you were in the lake and you went down deep and you could actually feel more and more pressure, especially on your ears, as you had more and more water on top of you. And right now, I want you to imagine that you're actually at the bottom of an ocean right now. You're at the bottom of an ocean of air because you're pretty close to sea level. Charlevoix is around 600 feet above sea level, depending where you're at. And so you feel about 15 pounds of pressure on every square inch of your body. Now, as you go higher up in altitude, there's less air on top of you. And so, of course, this pressure would decrease. All right? So, and we'll talk more about that in our class as far as altitude and things like that. 14.7 psi is the same as 760 torr, or millimeters of mercury. All right? And that is the same as 101.3 kPa. The magic of cameras. All right, and trying to write underneath them. All right, so here are some units and standards that you need to kind of keep in mind. All right, when it comes to pressure, these are all the different units that we're going to use, we're going to talk about. All right, you'll probably see more of these in your college chemistry class, millimeters of mercury, torr, for sure. You might use more kPa, and PSI, I throw that in there because think about your bike tire, think about your car tires. You know, your car tires, they want you to inflate them to right around 35, maybe 40 PSI. And that means that inside your tire, if you could go inside of your tire, every square inch of your tire would have about 35 pounds of air pressure pushing against the inside of that tire and giving you, giving the tire some form so that it could actually ride down the road and you wouldn't be on the wheels, the rims of your vehicle. So let's take a look at this problem again, okay? We've got our volume, we've got a pressure right here. 720 torr, oh, that's less than our 760. So we might be higher in altitude here because we have a lower pressure than the 760. This is a pressure, I'm gonna write P1, at a temperature of 35 Celsius. Okay. So one thing about our equations here when it comes to gas laws is we are going to want to convert Celsius to Kelvin. All right, remember it's not degrees Kelvin, it's just kelvins. So when we do that, here, do you guys remember how to do that? Anytime you have a Celsius temperature, you add 273 to that Celsius temperature to get a Kelvin temperature. So 35 plus, and I'll just kind of squeeze that in there, 273 is going to give us 308 Kelvin. So now I've nailed down my first temperature, my first volume, my first pressure, and it wants to know, hey, what's going to be the new volume? What's going to be the V2 at standard temperature and pressure? Well, that's a new term for you. Standard temperature and pressure. And we're just going to abbreviate that by writing STP. And that is Stone Temple Pilots. Not really, actually. Do you guys, anybody familiar with that band? If you're familiar with that band, I will be impressed. That is a band from my childhood, teenage years. We're talking back in the day. So Stone Temple Pilots, no, this stands for standard temperature and pressure. And when you talk about gases, when you start to do calculations with gases, you have to make sure that you are taking into account the temperature, the pressure, and of course, all of those things if you're trying to figure out, let's say, a volume. And this is going to make more sense here in a little bit. But standard temperature and pressure is the temperature and pressure. Again, standard pressure would be at sea level. So STP is going to be, we'll reference what we just set up here. STP is going to be 760 torr. And standard temperature is actually going to be 0 degrees Celsius, or, of course, that's 273 Kelvin. So what they're saying here is, hey guys, what's the new volume at this T2 and this P2 right here? If you were at standard temperature and pressure, what's the new volume? And if we look back at the combined gas law that we talked about on our note sheet right here, that's what we want to use. Look at this. We have P1, we have V1, we have T1. We don't know what V2 is, but we do know P2 and V2, or sorry, T2. So let's set up our equation really quick. All right. Again, I know that my, and I'll just write it over here to the side. We're going to be using P1, V1 over T1 equals P2, V2 over T2. Okay? So my P1, I'll make sure I have enough room here. I'm going to squeeze this in. My P1 is that 720. I'm going to put in there torrs. My V1 is going to be 2.8 liters. My T1 is going to be my 308 Kelvin. What don't I know? I don't know my V2. I'm going to write that right there. I do know my P2, which is 760. And I do know my T2, which is 273. Now check this out, class. I need to rearrange this equation to solve for V2. And basically to get V2 by itself, I'm going to multiply V2 by the reciprocal of this, right? I'm going to flip 760 down here, move 273 up here. And when I do that, right, I'm going to put 273 here, 760 here. I know it's kind of getting confusing because I'm getting smashed over here, but you'll notice they cancel out. Of course, whatever I do on this side, I've got to do on this side. All right, so my 273K is here. I'm going to extend this out. And my 760 is going to be right here. I'm just going to put a little T in there for torr. And here's why I did that. I'm going to show you. Watch the units cancel out. This is beautiful. Here we go. Torr, gone. Kelvin, gone. And when I get my answer for V2, it's going to make sense that only liters, that's a volume unit, is left over. So I'm going to multiply 273 times 720 times 2.8 divided by 760 divided by 308. And when I do that, scoot on over here because I'm running out of space. When I do that, my V2 is going to be equal to 2.4 liters. That's how you use the combined gas law. All right, that's how you use the combined gas law. All these problems are pretty much like that. Okay, all these problems are pretty much like that. Let me do one more for you. Because again, these problems, there's not a lot of variety other than solving for a different variable. You might solve for T2. You might solve for P2. Okay, so all of them are pretty much the same. Actually, just to keep this video short, I'm gonna end with that and just tell you the answers that you should get for number 2, 3, 4, and 5. Okay, so for number 2. You should get, like T2 here is what you need to solve for. You're going to get 330 Kelvin. But don't forget, this has to be put back into Celsius. If you were given a Celsius temperature in the beginning in the problem, it's good practice to put it back into Celsius when you're done. So I'm going to subtract this to get my 57 degrees Celsius. All right, you can hear my kids in the background having a great time. Number 3, 850 torr is what you're gonna get for that guy. That's your P2 that you had to solve for. Write that in there for you. And then number 4, you're gonna have a V2 of 2.6 liters. Is this bothering you right here? I bet it is. It's kind of bothering me. It's still bothering me. See, I just can't do anything about it. We already sealed that ship. Number 5, last and least, I'm just going to give you the final answer, 37 degrees Celsius, and that was solving for T2. All right, give these a try. Try to get them done before our meeting, and that way we can talk about them, make sure that you're feeling good about using the combined gas law to do problems that involve Boyle's law, Charles' law, and both of them combined. Hope you guys are doing well. We'll talk to you soon.